Alright, so we'll have a look at how we graph this, and then after that I'll show you how you find the reciprocal function of this guy. So looking at this, how could we describe the function? It's a function over a function. It's a linear function over a linear function. Have we graphed anything like this before?
No.
Not in this form. Technically we have, but this form of it we haven't. So the way in which we can graph things like this is you've got a linear over a linear. The way we can do this is we can simplify it. Now you've got a few methods at your disposal. You could do polynomial division, which you already know how to do from year 10 and from the start of the year. And we went through it in year 11 as well, didn't we?
No.
Oh, we did in year 10.
No.
And we did it at the end of last year. So you could do polynomial division, but for something like this, it's a little bit overkill because it simplifies really nicely. What I'm going to show you is something called the partial fraction method. The way you can do this is, you can think to yourself, all right, let's try and force factors of x plus 2 here. So I'm going to go along Vinculum, and I'll go x plus 2. Now, have a look at front here. You've got a 2x. So what I'm going to say is I'm going to say, grab this x, and I'll say it's x plus 2. Now, if you think about this, if I expand it out, it's going to be 2 x's, and then this is going to be 2 times 4. Where did the 4 come from? I giveth. Now, if I giveth, what must I do? Taketh. And then, have we done anything about that 3? No. So all of a sudden, we've got this in a partially factorized form. Moving along, we're going to go, oops, we'll split this into 2.
So what was your reasoning of doing the 2, make it 2x plus 2?
You're about to say. Well, you can.
Brad's already looked ahead in the future.
But
Okay. What was the point? Well, the point is, udus.
Oh. Right.
And then you simplify that. So this is going to be 2 plus minus 1 over x plus 2. This is like a hyperbola of some sort. So it's negative 1 over x plus 2. And then you've got a plus 2 here. Perfect. How good does that look?
well, that's easily graphable.
It looks easily graphable when it's in this form. So we end up getting f of x was equal to 2x plus 3 all over x plus 2. But when you use this partial fractions method, do it in Word. What you find is that you can put it in a form that's actually easily graphable. Now looking onto this, let's have a think. What are our asymptotes here?
Number 2.
What is our vertical asymptote going to be? Yeah, because if we put in negative 2 here, we end up getting what I call a pole. So it's like a straight vertical line. So there's going to be an asymptote at negative 2, or x equals negative 2, and the y asymptote is going to be at 2. Moving along. When we graph this, oops, what we discover, and I'm only going to sketch this, and by sketch this, I'm going to take it back a notch. First thing I'm going to do is I'm going to draw in my x-axis. And what I want to do is get some symmetry here. In the middle of my graph, I'm I'm going to say that's minus 2. Now if that's minus 2, then over here can be my origin. My horizontal asymptote, where was that? 2. Alright. Now, this is a hyperbola. So it's probably going to look like, and I'm going to do this one in green.
Is it a negative? So you're supposed to go outside?
The blueprint for a hyperbola looks like that, doesn't it? But as Mr. Sweets excellently pointed out, this one's negated, isn't it? So, what is the transformation on a negated one?
It's the other side.
Yeah, you turn that frown upside down. Is that cool?
So what do you mean negated? Like, why do you?
See how there's a negative in front of the hyperbola?
Yeah.
It's kind of
What's happened is,
Oh yeah.
it flips it about its asymptote, or it's, it flips it about its horizontal asymptote. And then there's one more thing I need to add to this graph.
The equation.
Yeah, this black line over here is y equals f of x. What about my green equation? Does that have an, or green line, does that have an equation?
negative.
Yeah.
So you don't actually have to write that, but you just write y equals x.
We don't even need that green one, to be honest. You should put in this guy here because you're going to get multiple functions on the one set of axes a lot of the time
Yeah.
with what we're about to do. Okay.
It's the same section.
Next thing, we're going to think about the reciprocal. Where are we? We've looked at reciprocal functions where it's 1 over, but what would the reciprocal be of this guy here?
I don't know. What is
Reciprocal, is it spelled with an AL or OL?
It's like that.
Yeah.
Okay. Okay, think about reciprocal. For a reciprocal function, when f of x approaches infinity on a function, what will the reciprocal do?
Or 0.
Oops. From which side?
Yeah, which side right?
The right side.
So when it's at positive infinity, then you're probably going to see it touching at 0. And then similarly, when f of x approaches 0, I will just leave that off. When f of x approaches 0, what does the reciprocal do?
Approach infinity.
It approaches infinity, either positive or negative. Okay, so let's think about this. This function, at this asymptote, it's approaching 0, isn't it? The reciprocal should be approaching 0, shouldn't it? So it might look like there, but it won't be. And I'll explain why after. Now what about when the functions here and here are getting closer to their asymptote? What will the reciprocal do? Further away from the asymptote. So I'm just going to tell you straight out now. Normally we'd place it here, but I'm going to place it here. And then I believe we're going to go, this one will look closer like that.
It's linear.
It will be linear because think about it. Look at the hyperbola side of that black function.
Oh.
Does that make sense?
Yeah,
So what we end up getting is, let's just say, I won't say 1 over f of x, but what I will say is, if f of x is that, let's say that g of x is going to be, I'm going to get this guy here, I'm going to flip it upside down, and then I'm going to just get this, what would we call it, this constant here, I'm just going to tack it on. And what you end up doing is negative x, take 2 plus 2, and therefore we should get negative x plus 0, or just g of x equals 0. Because this is sketched, it's not as accurate as it could be. It's going to be like that. Sorry.
So it always has to pass through the intersection of asymptotes.
Yeah, it typically always passes through there, and then it will give you the y-intercept there. You can see it's a negative gradient.
Yeah.
Does that make sense?
That third one that was.
Basically, yeah. Does that make sense?
Yeah, so there's a lot of drawing on this topic.
Quite a bit.
Yeah.
I mean, the title is Functions and Their Graphs.
Is it g of x equals 0, g of x
Yeah,
equals
negative
negative
x.
Oh, sorry.
Yeah, that's gonna love.
I was just checking to make sure you're paying attention because I wasn't. Does that make sense?
Yeah.
So what we've looked at on the far left, we've had a look at how to move functions into a graphable form using the partial fractions method. Then after that, we've had a look at graphing, and then we've thought about the reciprocal and what it would look like, and then an analytical way of doing it. Is that okay? Do you want something slightly higher order now?
Yeah.
Okay. Let's go. Right.
What's he doing? Just this one.
It's doing him.
You reckon he lays his back on his leg for that reason? It should not take you that long to grab a calculator. I couldn't find them.
Really? Why did you just decide to get into that now?
I'm able to pull the lesson.
Alright.
Well, it's breaking.
That took you 30 minutes to decide to get into that. Still a little bit lost there.
Okay, so those are 2 rules for now. What we want to do is we're going to graph. Oops, where are they?
I'll literally say the more flash.
Yeah, that looks alright. Rough.
Two fences.
Um,
One for emergencies.
Yeah, okay. It's hard.
Yeah.
Oh, yeah, I suppose.
Oh, that's.
Oh, that was fence.
I didn't bring my bag there. No, okay.
I'll need a back, guys. Alright, you can back.
Yeah.
Ready?
Maybe shower. Yeah, you have this one, to be honest. Actually, I want this one.
And then back again.
What if we want to graph something like this?
Too bad.
It wouldn't be too bad.
Oh, good one.
Any ideas?
Maybe, oh yeah, that's a,
What sort of function is this?
quadratic. Reciprocal quadratic, I don't know.
It's a constant over a quadratic. Or a second order polynomial. Do we know what those look like?
They're like this. Smiley face, frowny face. Type deal. Smiley face and frowny face, you know.
Well, yeah, the quadratic, so second order polynomial, it's either going to be frowning or it's not going to be frowning. So do we know what the 1 over would look like?
It's like 2 hyperbolas.
Yeah, it's like 2 hyperbolas and whatever. Now, if I said I want you to sketch that, don't worry too much about the values it cuts through. Would you be able to sketch this?
Yeah.
What's that?
Yeah?
Yeah.
Okay.
That's
I like this. Okay, what would you look for, madam?
Asymptotes.
Asymptotes. What are our asymptotes going to be here?
For the x, it's going to be -73.
Why is it 2x?
There's no factorable.
Okay, it's going to be at x equals -2 and x equals 3. So you've got 2 asymptotes there, or as I like to call them, 2 poles, because they're pointing straight up. What about the y asymptote?
Just still y.
Are we going to have any asymptotes here?
No. Yeah.
Is there any value that we can't get out of this function?
Zero.
0.
You get 0 and
Okay, so let's go for it. I think we've got all the info we need here. There's our Cartesian plane. Where are our asymptotes at?
X equals -2 and x equals 3.
X equals -2 can be here. X equals -3, that's, do you agree?
We'll just 3, yeah.
And then we've got the vanilla y equals 0. That's our positive x, that's our positive y. All right, now let's think about this. If we were to draw the quadratic, what would it look like? The quadratic, x plus 2, x minus 3.
maybe. Madden?
Which one is?
Is it going to be concave up or concave down, the quadratic?
But since it's the reciprocal, it would be down.
Think about it, if you expanded this out,
I don't know. Let me compare about.
what would that be, expanded? X squared plus,
It's take x.
take x, minus 6. Is that concave up or concave down?
Oh.
Yeah, so happy face or sad face?
Happy face.
Happy face.
Yeah.
Where's it going to cut?
The 3s and the 2s.
There and there. So,
That is normal quadratic.
1, 2.
Arbitrary.
Where's our minima going to be, or our apex? Midway between these two. Probably somewhere around there.
Yeah, like 1.
I'm not sure. Probably. I'm probably not going to think that too hard about it. Okay. Awesome. Now, we're almost ready to graph. This is what that quadratic would look like if it was graphed. But we're not graphing the quadratic, we're graphing the reciprocal of the quadratic. Think about it. When our quadratic hits 0, our inverse or reciprocal function is going to do what? Up here. Goes to infinity. Now the question is it going to be positive or negative infinity?
It's going to be positive infinity.
Why positive infinity?
You go smiley face.
Because you've got a smiley face. If this is positive, the reciprocal is probably going to be positive. So we're going to be here. As the reciprocal gets really big, or our quad gets really big, what happens to the reciprocal part? It gets really small, because it's, as it says over there. And you're probably going to get symmetry over here.
Why is the symmetry like that?
Because as this gets really big, did I get that wrong?
No.
Oh yeah, that's fine. So it's 0 there. So think about it as we read left to right. As we're over here, the quadratic is huge. Like it's grown immensely. Because the quadratic's really high value of y, this reciprocal has to be really low value, close to 0. As it approaches the asymptote, the quadratic gets small, but the reciprocal gets really large. You see? And because this is above the y-axis or above its asymptote, this will be above as well.
Okay.
Sometimes it's not always going to be like that though, but in this case it will be. Okay, what's going on here though?
I don't know.
It's gonna be radicals.
Yeah. So, I'll put it in. As we're approaching 0, we're below. So we're going to find, looks roughly like
But
that.
is it actually Is it actually?
What do you mean?
Or do they just go off into infinity and do the same? Or do they actually stop there?
No, it goes up like that. Now, think about it. What is this here? What do we call it? It's from stage 1, local minimum.
Yeah. Oh, that means that's like
What about, if that's local minima, what does this become?
Like
Maximum.
Local maxima
maximum.
or maximum.
It'd be maximum. There's like 2 maximums then.
Fine.
Oh,
Local max and local min. How does that sound? Best of both worlds.
sorry.
So based on that, what 2 more rules do you reckon we can add to this up here?
Local max and local min.
Local max
are all the same.
of
X-axis.
f of x becomes local min of reciprocal.
Yeah, it does.
Is that alright?
Yeah, they're supposed to be touching.
No, they don't touch in this one.
So why is local max the same as local min, but they're not the same? You know what I'm saying?
The values of x.
Oh, the value of x is the same.
Is that okay?
Yeah. So Matt, that would actually care with the y value, everyone just cares with the x value. Why is that? Everyone just cares about the x value, not really the y.
Because you can generate the y values based on the x values. Sometimes they'll overlap. So the one in the textbook, they touch. That touches that. The example I just gave you, it doesn't work. How do I know? Desmos already told me. But it's based on the rule. The local maxima will typically appear, the local minima will typically appear at the x value of the local maxima when you're working in this manner.
Yeah.
So the skill we're trying to pick up here is, can we graph anything that gets thrown at us?
No. It's
So
can.
should the local maximum be the one point?
Could you explain that in a bit? Or
Like, see the local minimum and the local max, should
Yeah.
they be just the 1 point there?
no, not on this case. It's just a similar value of x.
So for the rules, are just local maximum of x is a similar value of x to local min?
They share the same value of x.
And the reciprocal or imaginary quadratic.
The reciprocal of a quadratic will look like that.
Always.
The reciprocal of a cubic will look different. But it's the idea of how we're approaching this. So the rules in blue over there, basically, as f of x gets really large, the reciprocal of f of x will get quite small. As f of x gets quite small, the reciprocal will get quite large. It could be in the positive direction, it could be in the negative direction. You have to figure it out based on what your original function's doing. And then, to extend upon it, when we're dealing with stuff like this, where you're going to have turning points, your local maxima will coincide with the local minima, and vice versa. Does that make sense? So some of the questions you're going to do today will be algebraic. Some of the questions you do will just be the graphs, and you have to fit the graph based on what you see. So it's an understanding question. Is that all right? Okay,
Yeah.
so 3 things. One, we briefly looked at, or we reviewed, how do we graph hyperbolas using the asymptotes. We then looked at the partial fractions method. Do we remember it? Make sense? And then we had a look at the rules for graphing the reciprocal. So you're able to graph by eye if you need. All good? Alright, so the questions that we have for today should be accessible using the information we just looked at. What we'll do towards the end of the lesson, we'll recap, and then we'll have a look at how calculators can help us in this instance.
Yeah.
Cool?